Okay, so now we've seen how to use the sledgehammer. Okay, the sledgehammer is the full integration of our density function. Okay, the weight, the load intensity, or whatever we want to call it. Many of your problems are going to be simpler than that. Okay, and they're going to take advantage of a shortcut that I'm about to show you here. All right. So here, our density function is really in two pieces. And we can cut this thing right here, just like this. Okay. And so we're going to have some force here. We're going to reduce the load to some force there. Maybe we'll call that R2. And over here, we're going to reduce it R1. And we'll put it at that location there. Okay. So how do we find the magnitudes, and how do we find the locations? So let's begin with R2. And I want to remind you that the way we do this is by thinking about the area under the curve. And so our intensity function, or our density function, W2, is constant across that whole thing. All right. So I've just got an area here. So if I want to know the magnitude for R2, I can just use base times height. And so that's going to give me an 8 times 150, and that has a value of 1200. Okay. So that's the magnitude of that little section right there. Okay. Now, where is it going to be? Well, it's rectangular, it's symmetric, and if your intuition is telling you it should be smack dab in the middle, you, sir, are or ma'am, are correct. Okay. It is. It's right in the middle of that thing, right where I've drawn it. And so we would locate that over here. That's going to be 4 feet from that point right there, or 10 feet away. Whoops, that's funny. 10 feet away from point A, just like that. Okay, so rectangles, pretty easy to deal with. Now let's look at the other one. Okay, so we've got a different density function over here, W1. And so what we're going to do is I'm going to work it out pretty generically. So first we have to figure out what to put for W1. Okay. And it's going to be the rise. It's linear, so we need a slope. So we need a rise over a run. Now I could put 150 over 6, but I want to do this generically. So I'm going to call it height over base. Because a really cool thing is going to happen. I want to show you, and it applies to any situation like this. Anyway, there's my slope. So it's linear. So I've got mx, just like that. Okay. Now, the area is just going to be the area of that triangle. I don't have to do anything fancy. So we can just right away, we can say R1 is just going to be 1/2 base times height. And so for this particular case, then that's 450. Okay. Um, Now let's calculate the moment. All right. So remember, we're going to do a little dm. And so we're going to write that as xw1 dx. And if we integrate all of that, we're going to end up integrating height over base x squared dx. And our limit's going to go from 0 to b. Okay, now once we work that out, we're going to see that the moment is actually 1/3 hb squared. Okay, and in our particular case, that works out to be 1800. All right. Now, to locate it, we're going to use the trick we did before where we said that the resultant moment was some distance times r. Okay, and so that means that that distance is the moment divided by the magnitude of the force, just like that. But now let me use our generic expressions. So that distance mr is 1/3 hb squared, and r was 1/2 h times b. So this is kind of cool. You can see that the height of the triangle doesn't matter. I'm going to lose a b, just like this, and we end up getting 2/3, when I simplify it, times base. Okay. Now, 2/3 of times base means it's actually over here, like this. So our base is 6. 2/3 of that is 4, just like that. Okay. So there's some of your homework problems that you're going to have to do the integration, like in the last video. But a lot of them are going to be like this. You're going to be looking at it, you're going to put it in segments, and then figure out for each segment what's the magnitude of the force and how do I locate that force. And most of the time, it's going to be combinations of rectangles and triangles. Okay. So now that we know the triangular portion and we know the rectangular portion, what do we do from there? At that point, it's just like the problems we had before. I've got R1 here, 1200. Oops, just kidding. That one's not 1200. That one's 450. And over here, I'm going to have my 1200. And we know that the 450 is over here a distance of 4. And the 1200 is over here a distance of 10. So now that I've got those two forces, I can add them up to find the uber force, so to speak. Okay, big giant purple force. Where are we going to put that thing? Okay, the resultant, and we can figure out the moment from the 450, the moment from the 1200, and that's going to help us know where do we put our big giant uber force, like that. Okay. So I'm not going to work that out. You can do that. You've done a whole bunch of those already. What I want to do, I want to finish out the video looking at a few more of these examples, showing you how to break them up and that sort of thing. Okay. So let's get to this one. All right. Here, it's pretty obvious. We want to break it up like this. And so you're going to end up with, let's say, an R1, an R2, and an R3. Okay, just like that. And then find the moment for each one of those, add all that up, and that's going to tell you where we need to put our big uber force, our resultant force. Okay. The next one. Okay, here we've got two triangles. And so we'll cut it right down the middle. And one of those is going to have a resultant over here. Maybe we'll call that R2. And then the other one's going to be over here. We'll call that R1. Okay. Now, just a little note about where to locate those. With triangles, it's always located 2/3 of the distance from the pointy bit. And so that means that location is 2 from the end there and 4 from the end over here. So that's how you can know where R1 and R2 are. Okay. Pick up a couple more. Okay. In this case, what we'll do is we're going to cut this thing this way. And we've got a bottom part, which is going to have a magnitude. Maybe we'll call that R1. And then we'll have the top part up here. And we'll call that maybe R2. Okay. And R1, of course, is, oh, shoot, I'm so sorry. There we go. Now you know what I'm talking about. Okay, so what I did was I cut this thing right through here. So I've got a rectangle on the bottom, got a triangle right here. R1 is my total force for the rectangle, and it acts right in the middle, so at 3 feet from the end. And R2 is with the triangle, so I use 1/2 base height to get that, and it's 4 feet from the end. Remember the height on this thing, okay, is not going to be 200, not for my triangle. It's only going to be 50. Okay. Then I've got a third force, this guy right here. So when I get ready to find my uber force, then I've got R1, R2, and the 500. So I've got those 3 different forces that I've got to work with to find my overall force. And finally, this guy here. Different ways to break this up. Here's how I would do it. I would cut it right through here. Okay, and then that's going to give me one from the rectangle and one from my triangle part, just like that. Okay, so these are very straightforward. You know, look for these rectangles and look for these triangles. If you have an actual function, then you may have to go back and do it with this method that we did here, and just follow this pattern if you have something like that. They're pretty straightforward. Okay. Alrighty.